can be done in remote sensing and GIS-based techniques. Now, coming to these the spectral regions, which spectral regions is important for mineral identification, for this mineral exploration? Like in case of visible and near infrared, for example, 0.4 to 0.7, this visible range, and 0.7 to 1.5 micrometer, this is the near infrared range. Now, these two ranges are useful for ferric and ferrous iron, manganese, copper, and nickel identification. Then short wave infrared, there are two windows, atmospheric windows. We have 1.5 to 1.8 and 2.0 to 2.4 micrometer. Okay, in these two windows, we can identify hydroxyl ions. Okay, like your hydroxyl mineral deposits. Okay, like your clay minerals, like your altered minerals, then carbonates. And thermal infrared region like 3 to 5 micrometer or 8 to 14 micrometer. There are two atmospheric windows are there. In this region, there are one more that is very subdued, that is this 17 to 25 micrometer, that is not very useful. So 3 to 5 and 8 to 14 micrometer are very, very useful for silicates and carbonates. Particularly, all the silicates have the characteristic absorption peaks in the thermal infrared region only. They do not have absorption peak in the visible near infrared or optical region or the short wave infrared region, only in case of thermal infrared region. Okay. Now you see, what's the comparison of the multispectral and hyperspectral? That is the reason why hyperspectral remote sensing is so important. And there are a lot of advancement has happened for the last few decades in hyperspectral remote sensing. There are the newer the satellite systems are coming, like Hyperion, now the Prisma. So different kind of data now freely available that you can download and you can process and you can identify the mineral. Yeah. And there is a special lecture on that, hyperspectral remote sensing and hyperspectral data processing for mineral exploration. Now you see that characteristic absorption peak of the mineral you can identify in hyperspectral imaging. Why? Because in multispectral, the bandwidth is very, very wide, very large, where this narrow absorption peak cannot be detected. Okay, only the broad absorption peak can be detected. In case of hyperspectral remote sensing, because there are more than 200 bands, and the bandwidth is very, very narrow, 10 to 15 nanometer. So it can be very meaningfully, it can be used to identify the mineral based on its characteristic absorption peak. Like you see the spectral profile of the same minerals in multispectral imaging and in the hyperspectral imaging. You can understand that mineral can be identified easily in case of this spectral analysis of hyperspectral remote sensing data. Now coming to the hydrocarbon exploration. Hydrocarbon means there is a coal and the petroleum, but in this slide we are discussing only about the this petroleum, like oil and natural gas. And in case of coal, it is not so much required to use this remote sensing for exploration of coal, because coal is a bedded deposits, and if you can identify there is coal, then generally it occurs continuously. Sorry. So, but there are sometimes there are some faults which displaces this coal seam, so that needs to be evaluated based on some boreholes. But now in this present slide, we are discussing about the this oil and natural gas. Like you see, first the beginning is the geomorphic signatures, and here you see the drainage anomaly. You can see here the circular drainage anomaly, isn't it? That is indicative of the presence of a structural trap, that is a subsurface folded structure which can host this oil and gas. Okay, so from this circular drainage anomaly, we interpret that there is a structural trap or the subsurface folded structures which can host oil and gas. Then we need to go for the geophysical investigation like seismic survey. Then we'll be more you're confident it can be confirmed well. So this seismic survey was done, and then you can see what is this geometry of the structures. The yellow is the this top of the producing horizon. That is the top of the this structural trap where this oil is accumulated, and this black one is the faults. So through this fault, this oil and gas can come out. But here, this is the top surface, and above this is the impervious layer, so oil cannot come out. Okay. Now this is the actual interpretation what is done by the ONGC, and this is the actual interpretation of the structures. This kind of structure is there in this particular location that is very near to the Silchar in the northeastern part of India. And then followed by that, you have to drill here to see whether oil or gas is available or not, and then finally the production of oil and gas. And at this moment, this oil and gas is being under production in this particular location. See, in some cases, you can find this oil is seepage is happening at the surface. So oil droplets can be observed at the ground because of the oil seepage. So this oil has a characteristic absorption peak, 3.5 micrometer to 3.03 micrometer. So this is in the thermal infrared region, but it has also a absorption peak. In fact, two absorption peaks, secondary absorption peak in 1.7 and 2.3. Okay, and considering this 1.7 micrometer absorption peak, there is one hydrocarbon index has been developed by Quinn et al. And they have shown based on the reflectance and the wavelength of this absorption peak at 1.7, they have developed this hydrocarbon index, and based on the value of the hydrocarbon index at that particular locations, it is nothing but the reflectance in this particular bands. At that particular wavelength, what is the reflectance? Here, what is the wavelength? What is the wavelength here? Okay, and depending on the reflectance and their wavelength, this HI or hydrocarbon index has been calculated. Now, if the value of hydrocarbon index is very high, much higher than 0, okay, so then it is indicative that there may be some oil seepage has happened. Either oil seepage is there, or the soil is contaminated with oil. The soil is contaminated with oil. Similarly, you can also identify this vegetation stress due to this soil is contaminated with oil. If the soil is contaminated with oil, this vegetation in this particular region can be under stress, and there will be retarded growth. So that kind of the signatures can also be identified. Okay, so if the HI value is very close to 0, then there is no hydrocarbon, and if the HI value is very high, then there is hydrocarbon. This presence is very high. Okay, so you can tell that hydrocarbon is available there. That means oil seepage is happening. Similarly, this regional geophysical investigation like airborne or spaceborne gravity observation, for example, is also suggestive of these suitable conditions available at that particular location for the this production of the oil. That is the suitable cooking condition of the for producing oil from the microorganisms. Their thick pile of sediments is available, and so there is the low gravity, regional low gravity zone is indicative that there's a thick sediment deposits, because sediments are lower in density than the other rocks, no, igneous rocks or metamorphic rocks. So and also if there are the huge deposits of oil and gas, you know, it is even lighter than the water. So here the gravity will be much less. So these are indicative of the ideal cooking condition for this production of oil, for the origin of oil, as well as these accumulated oil locations. Now you see, this is the in situ spectral measurements and analysis can be done. This is the instruments, that is the spectroradiometer in the visible and infrared region. So you can use it for 0.4 to up to this 2.5 micrometer, okay, or even up to 3 micrometer. And this is for the thermal infrared region, okay, that is from 3 micrometer to 15 to 16 micrometer, or sometimes even beyond. This is particularly useful for these silicates, carbonates, and the hydrocarbons. And this is for other minerals like oxide, hydroxides, okay, the sulfates, so many other minerals. Now coming to thermal remote sensing, see here, thermal remote sensing is the wavelength region is 3 to 35 micrometer, is popularly known as the thermal infrared region in terrestrial remote sensing. Here in 3 to 35, you see here 3 is here and 35 is somewhere here. Okay, so here you see there are the atmospheric windows available. In one is 3 to 5, another is 8 to 14, another is your 70 to 25. But you see this prominent atmospheric window is at 8 to 14 micrometer. 3 to 5 is also good atmospheric window, whereas this 70 to 25 is a very subdued. Atmospheric transmittance is much less. And most importantly, this 8 to 14 micrometer wavelength region is very important for terrestrial this thermal sensing. Why, you know? Because at ambient temperature of the Earth surface, the maximum radiation from the Earth surface happens and around this 10 micrometer. Okay, that we'll discuss in the tomorrow in the thermal and this microwave remote sensing lecture. But here you see, for terrestrial thermal sensing, this 8 to 14 micrometer is very, very important. But in this particular region, here you see the atmospheric transmission is very less. Why, you know? It is because of the ozone layer in the ionosphere. So ozone layer absorbs much of the thermal energy. Okay. So in 9 to 10, so this particular zone is not very good for satellite-based thermal sensing, but from airborne, you can do that. Okay, it is because it is below the ozone layer. So airborne platforms can use 3 to 5 and 8 to 14 the entire range, but spaceborne platforms generally use 10.5 to 12.5 or 8 to 14, but excluding the 9 to 10 micrometer. But you know, in case of 3 to 5 micrometer, there is a problem because up to takes place. So during daytime, there are a lot of reflected energy will come in and around the 3 micrometer region. So the reflected energy component will be much higher than this emitted energy. So it will be very difficult to separate this thermal energy from the reflected energy. So it is always advisable that use this 3 to 5 micrometer window only during the night time. During daytime, there will be a lot of contamination of the reflected this energy and the emitted energy. And thermal remote sensing is based on the emitted radiation, isn't it? It is not the reflected energy. Now you see, thermal remote sensing basically it is based on this Planck's law, and you know the Planck's law, what it tells. In Planck's law, the radiant energy is a function of the kinetic temperature of the material and wavelength of radiation. Okay. In fact, it is the relationship between the three these your variables. One is what is the temperature of the object? I mean the kinetic temperature or actual temperature of the object, and how much this energy is getting emitted because this object is of certain temperature, so it will emit some radiation, isn't it? Thermal radiation. So how much is the energy radiated? What is the temperature? And what is the wavelength of the maximum radiation peak? Okay, relationship between specular radiance in that particular wavelength region, how much radiation is taking place or how much is the radiated energy. Okay, then what is the temperature of the object and what is the wavelength of the maximum radiation peak. Okay, this relationship Planck has for the first time he discovered this relationship, and like this the remaining are all either it is known or they are constant. Like pi, you know the value of pi 22/7. H is the Planck's constant. C is the speed of electromagnetic radiation or speed of light. Okay, and here this your H is there, and here it is. I think this is KT. No, this is the K is Boltzmann constant. Okay, so there are two constants are there. One is Planck's constant, and there is the Boltzmann constant. It is K, not lambda. Lambda is here. Okay. Similarly, in this case. Now, you see, in thermal remote sensing, there are some physical parameters are important. In fact, there are the thermal parameters that we need to study. Based on that, we can sense thermally these different objects and the differential signatures we can appreciate, and we can separate the object or identify this object based on thermal signatures, like thermal conductivity of the material, the density of the material, thermal capacity. It is nothing but this this specific heat and density, specific and heat and density, then thermal diffusivity, and finally thermal inertia. And in fact, thermal inertia is very, very sensitive because it is the product of the thermal conductivity and the density and the specific heat that we can see in the thermal lecture. We'll discuss more on the thermal inertia and how thermal inertia is used to identify different these earth materials. Like in this example, you see, this is a multispectral thermal image. Means it is not a single band thermal image, but multispectral, depending on different wavelengths. Like here, band 5, which is the wavelength is close to 11 to 12. Okay, band 3 is around 10 micrometer, and band 1 is close to 8 micrometer. Okay, so now if the feature has a higher temperature, okay, if the feature has a higher temperature, it will radiate, the maximum radiation will take place at the shorter wavelength. Okay, if the material has the lower temperature, the maximum radiation will take place at the longer wavelength. Okay, that is the basis of thermal remote sensing. Okay, in the Planck's law or even in the Wien's displacement law, one can understand. And they have established the relationship. If the object has the higher temperature, they will have the maximum radiation, at the shorter wavelength. And on the other case, if the object has the lower temperature, they will have the maximum radiation in the longer wavelength. Now, if we use three different wavelengths, one is longer wavelength, one is intermediate wavelength, and the shorter wavelength. Now, if you assign colors like longer wavelength, you are assigning red color, and shorter wavelength, you are assigning blue color, and the intermediate one, you are assigning green color. Then what will happen? If the temperature of the object is high, then what will happen? It will have maximum radiation in the shorter wavelength. So then the object will look blue, isn't it? Blue. So this is a nighttime image. So that is why thermal inertia is important. So based on thermal inertia, hard and compact rocks, water bodies, they have higher temperature during nighttime. Whereas alluvium, that is alluvial fan, and loose Piedmont deposits, okay, these are loose unconcentrated material. They have the low thermal inertia. So what will happen? They will have the lower temperature during nighttime, but they can have the higher temperature during daytime. So that is why they appear, you see, this alluvial fan and the loose materials, they appear red color. Why red color? Because they have a maximum radiation in the longer wavelength. Similarly, in case of lava flows, you see, different lava flows we have, and these lava flows have different temperatures because they have been erupted at different times. Some lava flows are old lava flows, and some lava flows are very, very young lava flows. Okay. Now, if we make a FCC, false color composite of 531, the longer wavelength, intermediate wavelength, the shorter wavelength, then what will happen? The lava flows, those are comparatively young. Okay. They are comparatively hotter, isn't it? And then they will have maximum radiation in the shorter wavelength. So maximum radiation in shorter wavelength, that means in case of one, there will be maximum radiation. And if we assign this one blue colors, they will appear blue. So that means blue colored, these lava flows, they are the young lava flows. Whereas red color lava flows, they are the old lava flows. Why? Because they have assigned red color at the longer wavelength, and because their temperature is less, isn't it? Temperature is less, so maximum radiation will take place in the longer wavelength. So that is why they are appearing in different colors. So from this color of this multispectral thermal image, we can also identify that whether the lava flows are young or lava flows are old. So these are the some of the scientific advancements that happened in the last 1 or 2 decades. Now you see, thermal remote sensing for coal mine fire detection and monitoring. In this case, land surface temperature is very, very important. So we need to have a precise land surface temperature. And after we have this land surface temperature, then we need to identify these individual pixels, whether the pixel is anomalous or not, whether the pixel is higher temperature than the background. And if it is a higher temperature, whether it is different from the background or not. So based on these two criteria, whether the pixel has got higher temperature and whether the pixel is different from the surrounding background pixels, then we can identify this pixel is a thermally anomalous pixels and it could be a coal fire pixels. So this is how we can detect these thermally anomalous coal fire pixels. So these are known as the coal fire detection algorithms. So there are different bases of the algorithms. Okay. So first is precise land surface temperature, followed by this your coal fire detection algorithm. Then we identify this thermally anomalous coal fire pixels. For example, here you see, based on the pixel integrated temperature modeling, we have identified these are the thermally anomalous pixels and surface pixel coal fire and subsurface coal fire. Red is surface coal fire and this orange is subsurface coal fire that is shown here. But if you want to know whether it is this based on observation, whether this pixel is surface coal fire or not, for that you have to go to the shorter wavelength. So in shorter wavelength, it will give you higher temperature information and it can target exactly the pixel, whether it is high temperature target or not. Okay. So this is in TIR range, that is 8 to 14 micrometer, rather 10.5 to 12.5 micrometer range. We have identified the surface and subsurface coal fire by modeling based this approach. And here it is by actual observation in the shorter wavelength, short wave infrared bands. Okay. Landsat short wave infrared band. Then this particular pixel is showing high temperature target or not. And we identified these are the point locations. They are indicating these are the surface coal fire locations. Now, using this surface and subsurface coal fire information, and there are other this mining, environmental classes like open cast query, like closed and abundant queries, there are the coal washeries, and many other classes. and the surface and subsurface qualifier, we have prepared the complete this your environmental indicators path or mine plan. Okay, so environmental impact assessment, at a one-time assessment of this area, and this is very, very useful for the monitoring of the mining operations and the reclamations. So coming to this the microwave remote sensing, rather the radar remote sensing. Radar imaging is an active illumination system. Now we are coming to the different spectral region. Okay, first we have discussed about the optical region, then we have discussed about the thermal region. Now we are discussing about the microwave region. And you know the microwave region is basically 1 millimeter to 1 meter, whereas synthetic aperture radar is 1 centimeter to 70 centimeter. Whereas in case of optical region, it is in micrometer, but in this case, it is centimeter, which means it is 10 to the power 4 times of this optical and thermal remote sensing. The wavelength, what you are using in microwave remote sensing, it is at least 10 to the power 4 times the wavelength of the optical and thermal remote sensing. Okay. Now you see in radar imaging is an active illumination system. You see here the red color is basically the transmitted pulse. So it is the your antenna is transmitting this radar pulse. So this is the active sensor. It is transmitting these electromagnetic pulses. Then it is coming down radially to the ground, sidewise from this satellite, and up nadir. The nadir is here. It is up nadir, isn't it? It is coming radially as the radial distance, then sidewise one side, and up nadir. Okay. Now this yellow is the backscatter radar signal. It is received after a fraction of a second by the receiving antenna. So basically radar, you know, radio detection and ranging. This is a ranging device, isn't it? A ranging device is it works based on the time when this pulse is transmitted and when the pulse is received. How much time is the difference between these two? The time is a measure of the distance, isn't it? So based on this time, you can resolve that it is coming from here, it is coming from here, it is coming from here. The different yellow, you see from different places, it is coming back, isn't it? So then you can process it and you can construct a digital image depending on when it is coming back to the receiving antenna and what is the signal strength which is coming back. Now there are many advantages in the radar system because it is an active system. It operates both day and night, particularly useful in case of polar regions. You know, polar regions, there are a number of months where there are both day and night, or both are night, isn't it? It's completely dark for some months. So for that, the radar sensor is very, very important because it does not need the solar radiation, does not need the sun. Another advantage is it penetrates through cloud, and also it penetrates through rain, as well as it penetrates through vegetation and ground. So you can have information about the terrain, even in the forested area. You can have information about the subsurface features. And most importantly, during the rainy season, you can have information. You can have image during the rainy season. It does not depend on the cloud. Whereas in case of optical remote sensing or thermal remote sensing, if there is cloud, you will not get anything. Now there are certain disadvantages also. Now see, this is the image of the Shillong Plateau. If this the pulse is coming like this is in this particular direction, the image will be developed like this. In this particular slope will be bright, the opposite slope will be dark. Okay, this side will be bright and this side will be dark. Isn't it? So now there are disadvantages. There is a speckle effect. You see there are granularity effect, isn't it? This is known as speckle effect. So granularity in the image brightness, that is known as speckle noise. That is one disadvantage. There are geometric distortion. You see that this particular slope gets shortened, and here there is not a problem. There are many these features are getting shortened, or the getting topographic reversal has happened. So there is the geometric distortion of the this feature happen on the image. Okay, these are known as foreshortening, layover, or radar shadow, or it is radar ambiguity. It is known as. And most importantly, it is not sensitive to color of the object or your composition, the chemical composition of the object, but it is only depending on the electrical properties. More importantly, it is depending on the dielectric properties of the material or free H2O content of the material, moisture content or free H2O content, or dielectric properties of the material. Okay. See, radar remote sensing for geoscientific studies, it is sensitive to surface geometry because it is side looking and this radial geometry. So it provides information more on geomorphology and geological structures. It is sensitive to surface roughness. It is very, very sensitive to surface roughness. So it is very, very important in the non-vegetated terrain, and it provides information on the lithology. It's sensitive to moisture content, okay, or dielectric property of the material. So it provides information on the unconstituted material, soil, okay, weathered materials, okay, altered mineral deposits like gosans, okay. And most importantly, it has the capability to penetrate through vegetation and ground. It allows image of vegetation covered terrain and subsurface geological features, for example, buried paleo channel, active fault in the alluvial terrain, and sometimes non-geological features, underground civil structures like water or oil pipelines, sewerage lines also you can identify. But for that, you need to penetrate little more. So for that purpose, you at this moment, this satellite-based radar cannot penetrate very deep. Only you can penetrate only few meters. That too, it needs very long wavelength. Okay. So in such cases, you can work with the ground-based radar imaging. Ground-based radar imaging or ground penetrating radar is also known as the GPR. So based on that, you can identify the subsurface features. Now you see what is the utility of radar remote sensing. If we merge this radar image with the optical multispectral image, you have both kind of information. It is a fused product of this radar image, SARC, and optical multispectral false color composite. So here you see lithological discrimination is very clear from the optical multispectral data. So different material composition you can identify based on this color. And geomorphology, it is getting highlighted because radar image has been merged. You can see the structural hill is so highlighted, isn't it? And this, you see this minor topographic relief variations also you can understand here. And most importantly, because it can penetrate, so buried channels here, you can see buried channels are also it is detectable now. This you see here, crater boundary is very, very sharp. Why? Because it is side looking. And most importantly, it is sensitive to the surface ruggedness or surface roughness. And that is why these aeolian landforms like longitudinal dunes are very clearly visible, isn't it? So these are possible because radar image has been merged with the optical multispectral image. Now coming to the geological hazards, this is one of the very important areas in geoscientific studies or geological applications. You know, these naturally occurring and or anthropogenically induced hazards of geological origin are known as geological hazards. Okay. In fact, these natural hazards are classified into geological, hydrometeorological, and environmental or climatic hazards. But we are interested in studying the geological hazards. Those are maybe internal and external these hazards. Internal hazards known as the endogenous, like earthquake, volcano, tsunamis. These are endogenous, isn't it? Because the force responsible for this hazard that comes from inside the earth. But this exogenous, this is like mass movement, like landslide, avalanches, rockfall, river bed erosion, road cutting. These are all because of the external factors. And external factors are basically controlled by the force of gravity. By the force of gravity, isn't it? Wherever there is topographic slope, then the mass is vulnerable to this your slope failure, provided the slope is this not below this angle of repose. When the slope is below the angle of repose, then it will not fail, isn't it? When the slope is stabilized, it will not fail. All slopes are not the unstable, or all slopes are not going to fail. But depending on the material composition, material this your geotechnical properties, as well as the topographic slope, that slope is important. And the force of gravity is the driving force for that. And then anthropogenic hazards like mining hazard, like coal fire, land subsidence, okay, roof collapse, and urban hazard like groundwater depletion, aquifer compaction, and water pollution. These are some of the urban hazard. Now you see of the landslide on the ground photograph, how it looks like a spoon. And on the satellite image, you can see. And this is basically showing that is how a rotational landslide looks like. And see, you are the trident-like shape. You can identify. This is basically the Uttarkashi landslide, Bornobad landslide at Uttarkashi in Uttarakhand state. And this landslide scar can be easily identified on the image. Now you see, this is the landslide hazard zonation or hazard assessment or susceptibility mapping. We can do it's not the different causative factors like what are the rock types, what are the geomorphology, what are the geological structures. Okay, and based on that, we can have an integrated map that helps us to understand that what is the potential of landslide, this your susceptibility in this area. Okay, this is the landslide susceptibility map. Here we showed that some of the areas are highly susceptible zone. That these maps we prepared in 2000 from ISRO. There was a project, National Landslide Project. Here we studied the major pilgrimage routes in Uttarakhand and major tourist routes in Himachal Pradesh, and where we have prepared this kind of maps, isn't it? And we have shown this very high or severe hazard zones. Here in Uttarkasi, we showed that this is a very high hazard zone. And in the next year, there's the massive landslide, and 2001 happened, isn't it? Again, we studied that very high resolution airborne image of 1 meter or less than a meter resolution, and we prepare more large scale this hazard zonation and this your management practices to be adopted. Now, in case of this landslide studies, it is important to understand this or detect the movement and the movement before the major landslide happens. That is when this landslide is showing slow movements before the major slide. If we can detect that, then we'll be able to forewarn that in the very near future, maybe in few hours or few days, this landslide is going to happen, isn't it? So continuous monitoring if we can do. So this is one such study, classical study. You see at different intervals, they have studied these movements, okay? And this is for 3 days interval. This is your 6 days. This is 9 days, 9 days, okay? Again, 12 days and 15 days. And you see each color cycle represents lambda by 2 land surface displacement. Lambda is used here. This 5.6 centimeter is the lambda. So lambda by 2 is 2.8 centimeter, lambda by 2. So each color cycle means 2.8 centimeter movements. So precise movements you can measure. Okay, the slow movement before the actual landslide happens, if you can detect, that helps you to develop an early warning system that in the near future it can, this sliding is going to happen, isn't it? And there are other model-based approaches like rainfall, just mapping this or this monitoring the rainfall over the days, okay, and antecedent rainfall for a few days. And if you sum up this rainfall, these measurements over this a particular area, then you can also assess that whether landslide is going to happen due to this rainfall or not. But landslide can also happen due to the earthquake because of the shaking associated with earthquake, and also because in the this your hydropower project, okay, where the all along the rims of the reservoir, sometimes there are small landslides can also happen. Okay, so here you see this is what we have studied in and around the this Terry, this thing your the dam. We have observed these slow movements are happening all the rim area of the Terry Dam. This is the classical interferometric SAR. Whereas in case of Nainital Lake also, this is the natural water body. We can see in some of the locations it is showing this land surface deformation, isn't it? So you can see here there are some the movement directions based on the direction of the movements. The color has been assigned from red color to the blue colors. In some cases, it is moving towards this the satellite. In another case, it is moving away from the satellite. Okay. Similarly, this if you have a coarse GNSS network, from the GNSS network also one can prepare this land surface deformation map associated with landslide. This is one such paper published in 2011 with this the network of the GNSS network. Okay, but there are GNSS more number of these core stations have been established by the Survey of India. Now is the permanent GPS station. This is based on campaign mode GPS observation. So that means at a particular location you have the these your monuments, and these monuments have been this GNSS observation has been taken a number of times. Now, depending on the movements of that particular monument, this kind of this displacement has been measured, and then finally all over this location, these many monuments are there. From all these monuments, if you have the displacement measurements from multi-temporal GNSS observations, then you can prepare this kind of displacement map. Okay. Now, landslide slip surface determination. Okay, by where basically this landslide is happening? Where is the slip surface? For that, we need to use geophysical techniques. So we have a lecture on geophysical and geodetic techniques. Okay. So add geotechnical characterization. These are very, very important for developing an early warning system. So you see, if you have geophysical investigation, you can map where exactly the hard rock available and above which the loose materials are slided down. And the slow deformation, if we can measure by interferometric SAR techniques, so integrating this kind of information can help us to model then when this landslide is going to happen and how this landslide movement will happen. The slip surface, what is the geometry of the slip surface, and how this movement of the material is going to happen. Now, if we, in case of earthquakes, see, in case of Nepal earthquake, you know, there is a 7.8 magnitude earthquake occurred 80 kilometers northwest of Kathmandu city on 25th April 2015. And there are many aftershocks happened over this area after this 25 April 2015, and many of them are above 6 magnitude. And one of them, you see here, it is 7.3 magnitude. It's quite high magnitude aftershock, isn't it? Now you see this land surface displacement due to such earthquakes can be measured by remote sensing techniques, remote sensing based geodetic techniques. Okay, and if you can this measure that land surface displacement by this, okay, then you can assess the what is the peak ground acceleration and what could be the potential damage. So this is how we have done it. That due to the main shock, this kind of land surface deformation we have mapped. Here is the uplift. Uplift is about 165 centimeter to with respect to the radar line of sight, and here is the subsidence, and subsidence is around 60 centimeters with respect to the radar line of sight for the main shock. And for the major aftershock of 7.3 magnitude, you see the affected area is much lesser. Here is the uplift and here is the subsidence. So geological characterization or the what is the fault responsible for that, that can be well understood from this displacement pattern of this main shock and the aftershock. See it? Here is the subsidence, here is the uplift. So uplift is 65 centimeter and subsidence is 35 centimeter. And the total area, this duration before the main shock to after the major aftershock 7.3, if we study the entire period, so this kind of displacement map, which is combination of these two, can be this obtained, and we produce that. And based on that, what are the seismic hazard, potential seismic hazard can happen, that we have studied, and we have a number of observations we have made. Now you see, based on the MMI scale, modified Mercalli scale, which is a scale which shows this impact of the earthquake in terms of the damage, okay, with the scale of 1 to 12. Okay, so here you see in case of Nepal, this main shock causes this kind of impact, and it is the main shock and the aftershock all together, this kind of impact has happened. Whereas in case of India, only certain lobes, this lobe, this area, there are some damages has happened. It's very, very characteristics, very peculiar type of this your damages has happened. So these are all controlled by the in situ factors, in situ geological factors. So geological factors are very, very important. What are the geological structures? What are the thickness of the soil there? What is the this your depth of the groundwater there? Okay, whether there is a ridge is there or there is a valley, isn't it? What is the material composition? The loose materials or is the hard rock? So all together are responsible for this differential damage. In some area more damage, some area less damage. Now, for understanding all such the seismic hazard, we need to have some kind of geophysical investigations. First, we need to identify what are the areas of active faults or the weak plains, whether the weak zones are available, and then what is the likelihood of the shear wave velocity. So for that purpose, we need to have this MASW survey or this engineering seismograph survey. It what it measures the shear wave velocity in the subsurface material. So this kind of this your observation we have taken, this survey we have made in the Indian part of this area with respect to the Nepal earthquake, and then we have identified these locations of the active faults and the shear wave velocity in the neighboring region. And based on that, the geological hazard map, rather seismic hazard map, has been produced. Now you see, for active tectonics, where these presently there are movements are happening all along the Himalayan foothill regions, you know, we have studied extensively by morphotectonic analysis, by this large drainage basin by the drainage anomaly in terms of drainage segment anomaly, drainage deflection, stream migration, and geophysical investigation like ground penetrating radar survey to identify where this subsurface, this your indications of the active faults. You see, here is the locations of the active faults. Here some kind of deformation we observe. Here the locations of the active faults. This is by geophysical survey we can map. Now, this another important area is the paleochannel mapping. So paleochannel mapping, there are the people are working with only the optical remote sensing or the digital elevation model. But here we have made an approach using optical remote sensing, using the topographic information, using the thermal remote sensing, and most importantly, microwave remote sensing. Why, because radar, microwave with a longer wavelength radar, it can penetrate through ground. And paleochannels, those are buried, particularly buried paleochannels, those are not visible on the surface. So if the electromagnetic radiation can penetrate through the surface material, it can give you information about the subsurface paleochannel. Now you see, this is the Landsat 8, this optical multispectral image, and this radar image, RISAT. It is ISRO satellite, RISAT, this fine resolution 2, okay, in SAR image. We have merged together. And in Kalimangan area of Rajasthan, there is the paleochannels of Saraswati. Is believed it is flowing in Kalimangan area. So that we have identified the locations of the paleochannels using the merged product of the optical and radar image. Now here, this land surface temperature is also very, very important, because all along this paleochannel, this temperature of the material will be low. Okay, so it is the regional temperature information coming from the MODIS. And then you see here the electrical resistivity tomography, ERT, geophysical investigation. Okay, so here what you can get information about the subsurface paleochannel, that is the saturated with water, isn't it? So this paleochannel information we can identify. Here you see all below the surface there is the low resistivity zone we can identify, and low resistivity means this is the riverbed, but the riverbed is now covered by the dry materials above the surface. Okay, so these are the buried paleochannel. Okay, so by electrical resistivity we can map that. So remote sensing, okay, optical, then your thermal, then microwave, then geophysical, like your electrical resistivity tomography or ground penetrating radar. So these are how we should have integration of that. Then we'll be able to identify the location of the paleochannel, and then there are different studies you can do about the previous paleochannel behavior, about the discharge at that time. Okay, what are this active tectonics, if there was any. So all kinds of study you can do. Now coming to this integrated spaceborne and ground-based geodetic observation for mining hazard like mining subsidence. Thermal we have already discussed. Now mining subsidence. Now you see, the coal fields. In India there are Gondwana coal fields. Are 54 prominent Gondwana coal fields are there. 54, and Jharia coal field. It is one of the 54, but the most important coal field. Why? It is the locations of the prime coking coal, very high quality coking coal. It's the only coal field in India. Okay, but at the same time, it is the worst affected coal field in the country. So there are a lot of environmental damages has happened because of the indiscriminate mining, particularly before nationalization, and after nationalization, mining has happened with reclamations. But even then, there are a lot of this damage has already happened. So that causes this mine fire is uncontrollable. But there are, to a great extent, it is under control. And there are many areas there are roof collapse or land subsidence is happening. So we have made an attempt to study that status of the land subsidence using multi-frequency approach, using C-band and L-band. And we have identified the areas affected by land subsidence and the rate of subsidence. Now this is this satellite-based interferometric SAR-based observation, and this is your ground-based labeling-based observations. Okay, so this is ground survey-based subsidence areas by labeling or this total station by the miners, individual colliery personnel or these individual mining area personnel. They have mapped this and identified this mining subsidence area and the fire area. This is required for them to monitor the mining operations or to operate the mining these activities, isn't it? So now we have compared these two maps and we found that many are overlapping, but there are many areas we have identified these are not mapped by them. Why? Because they are interested only in the mining area where they are mining at this moment. But this is our picture is showing you the in totality. Wherever there are some kind of subsidies happening, we have made a complete information of that. Now, integration of this satellite-based and ground-based geodetic observation is very, very important. For that purpose, we did, this is the collaborative project, okay? This multi-organizational project with Central Institute of Mining and Fuel Research, Dhanbad, and Survey of India. So these are the project teams from different institutions. So using the digital label, using the campaign mode GPS, and then we have integrated all these observations. And 4 test sites we have extensively studied. There are the 4 test sites. And one of these test sites you can see that is in Jairampur area. This is the locations. And here you see there are roof collapse is happening because of the subsurface coal fire and underground mining. And see laterally also there are horizontal displacement is also observed. And this is direction of the horizontal displacement. Now, if you make a comparison of the labeling based observation and the C and L band difference in interferometric surface observation. So this is the figures you can see. Okay, so around 13.59 is the labeling based observation and 12.5 in case of C band and L band is 18.2. Something they are quite comparable each other. Now coming to the groundwater studies. So in groundwater studies, there are groundwater targeting, recharge estimation, groundwater flow modeling, quality assessment. There are many, many newer areas are coming. For example, this you can see this is here quality, prospect and quality together, integrated information. Where the how much water is available, whether high water availability, and what is the quality integrated together. And it is only the groundwater availability, and it is what is the flow directions in the Dun Valley, in Dehradun and the surrounding areas. Now you see, for example, from the remote sensing image, particularly the false color composite image, one can primarily assess where the groundwater availability is high and where groundwater availability is low, where groundwater available near the surface, where groundwater available much deeper the surface. Those kind of assessment one can do. For example, from this image itself, we can tell that this particular area, you see soil moisture is very low, there is vegetation is not good, vegetation is very scarce, very less, isn't it? And on the river bed, there's no water. So that means all the waters are percolated down as a base flow, and water is not available near the surface. But if you go down to here, suddenly what appears on the river bed, isn't it? And you see there are a lot of vegetation. Red color is basically indicative of vegetation in the standard pulse color composite, and blue color is the presence of soil moisture. So you see here soil moisture is high, vegetation density is high, and water is coming near on the surface of the river bed. So all are indicative of this shallow surface, this groundwater availability, isn't it? So this is just from the image itself, you can have some kind of assessment where groundwater is available or not. Now you can do a lot of the studies by integrating different factors, different kind of observations are required, different kind of this your geological, geomorphological, and variables we need to integrate together, and then groundwater level information which is available from Central Groundwater Board and the state boards. Okay, and the rainfall and other information. If we integrate together, we can have much more robust information about the groundwater availability. And if you want to have the quality assessment, then you have to have the groundwater sample, you have to collect, and you have to do this analysis of that. Now, to confirm this availability of groundwater, we need to have this your geophysical investigation. Geophysical investigation like your vertical electric sounding or electrical resistivity tomography. Okay. Now you see here you see there is a dip of the resistivity, low resistivity zone, and on the ERT you see there is the low resistivity zone. You can see in the profile. So this is the area where the groundwater is very much available, because this is indicative the material which is saturated with water. That is the aquifer. Okay. Now very much happening all over the country because of this widespread groundwater extraction. Okay. Here that groundwater extraction can be mapped well by the gravity observation now. This is GRACE gravity. Okay. The GRACE gravity can tell you that where this terrestrial water storage assessment, and it shows that in the northwestern part of the country, it shows the dip in the groundwater storage change. There are negative groundwater storage change. assessment has been shown. I have not shown in the slide, but this in regional level, you can have information about that in the northwestern part of India, there is a lot of groundwater extraction has happened. That gravity shows. Gravity means mass. There is the mass has been decreased over the years, and mass decreased by how? It is because of groundwater extraction. And when you extract it and you are using it or in the irrigation, then it will be evaporate. So you are no longer getting this water. It is out of the your aquifer system. Now that kind of information you can prepare from this groundwater level, these observations. Okay. So is it pre-monsoon groundwater level, and post-monsoon groundwater level shows that groundwater depletion in Mohali Chandigarh area. This is the region is Mohali Chandigarh area. This groundwater depletion we are showing. This is Chandigarh. You see, this is Mohali, this is Landran, this is Kharar, this is Darabasi, this is Ambala city, Ambala Kant. Okay, so these are the locations where groundwater depletion has been very high. Both pre-monsoon and post-monsoon both are showing. Now, because of this groundwater depletion, aquifer becomes void, and because the compaction of the aquifer and the overlying confining layer is happening, and because of that, the land is getting subsided. Okay, and that subsidence we could measure well by the technique, interferometric SAR technique. You see, in case of Mohali, Chandigarh, Kharar, this Banur, Derabasi is showing these prominent signatures of land subsidence even up to 12 centimeters per year. Okay. Now this is this time series deformation history. If we study by advanced techniques, so you can see how the land surface deformation has happened over the years. Okay, in Mohali, Chandigarh, and this thing, and the most important is the impact. Because of this differential, this subsidence, the houses are under this soil and this structure interface. That means the ground and the structure interface, it is not stable. Somewhere it is going down, subsided, okay, and it is differentially subsiding. Because of that, there are a lot of cracks have developed, particularly in the masonry buildings, masonry house. These cracks are rampant, and different kind of cracks are there. We have studied that, like vertical cracks, then there are the horizontal cracks, and then the oblique cracks. In terms of the geometry or the orientation of the crack. Now, in terms of the stress mechanism, there are the cracks are like tensile or tensional cracks. Those are because of the pulling forces. Somewhere is the compressional cracks because of the compressive forces. In some cases, you see this is the tensile oblique cracks and it is compressive oblique cracks. In some cases, it is shear cracks. Now, there are different kind of in situ geodetic observations, and integration with spaceborne observation is important. Like here, our team is working like in GNSS observations. This is our this subsurface instrumentation and this GNSS monument over which we are studying it. And there are the small monuments benchmark we have developed, hundreds of benchmark we have generated, and this is the permanent benchmark. This is Survey of India benchmark. With respect to that, the labeling survey has been done by Survey of India and IIRS together. And this is the Survey of India team. Those have conducted this survey all over this Mohali, Chandigarh, Delhi, and different locations in Northwest India. And this is our team, the GNSS and this Survey of India. Not only that, we have also made some kind of the subsurface instrumentation like your vibrating wire, piezometer, extensometer we have installed, and based on that, what is the compaction is happening, that also we have studied. So now finally what I want to tell that not only the remote sensing based information, but different kind of geophysical information. There are other allied techniques like geodetic techniques, isn't it? Geophysical, geodetic techniques, and sometimes the chemical analysis, depending on the applications you need to carry out. And a lot of ground instrumentation is required, either in the laboratory or in the campaign mode in the field. So there are some glimpses of some of the instruments what we use. We have the direct shear test instrument, engineering geology, dedicated engineering geology lab we have. We have the spectrometer, we have the ground penetrating radar, we have the FTIR, that is in the thermal infrared spectrometer, we have the thermal imaging camera, we have the core station, permanent GPS station, we have the total station, we have the receivimeter, we have ERT, we have these portable weather stations, and many more. So a lot of ground instrumentation and field laboratories are important in association with the remote sensing based these observations. Okay, thank you. So after this, maybe we'll have a few minutes break, and we'll take up some questions from you, and then we'll try to uh, give you the answer to that. Okay, so maybe 1 or 2 minutes break. Then after that, we'll take up your questions. So our team. So maybe we can have a So, okay, friends. So I think you have enjoyed this lecture, and there may be many questions you have, but at this moment you are not in a position to ask many of the questions. So if there are some questions which bothers you in the future, so you can write to me. Okay, I have given my email address in the this last page of the slide. Okay, I can show you. It's rschatterjee@gmail.com. Okay, sorry, rschatterjee@irs.gov.in or rscirs@gmail.com. Okay, you can write to me. It is there in our website. You can find our email address. Okay, now let's taking up your questions. First is Surya Kaushik has asked that how do we merge the two data from radar and optical measuring instruments? You can do that. It is not very difficult, this technique. So there are some procedures is there. So you can merge any kind of two data. For that, your spatial resolution should be comparable, similar spatial resolutions. And if you want to replace, like in a multispectral image, you have a FCC, full scale composite image. So then you generate this intensity hue saturation, then intensity, this component can be replaced by thermal or microwave, any single band image, you can use it for replacement. Okay, that is one way. There are different other techniques, multiplicative techniques. Then it is the statistical techniques and color transform techniques. IHS is a color transform. Then there is the statistical one and multiplicative techniques. So different techniques are there. Based on that, you can merge two sets of data. Okay. Again, Surya Kaushik has another question. Suggest a good book for resource for learning. So there are many books are there for remote sensing for geosciences. There are two books are very, very good. One is Sabin's book, Remote Sensing for the Geologist. Another is from the Indian authors, R.P. Gupta. He was the professor of IIT Roorkee. R.P. Gupta, that is the Geologic Remote Sensing. These are the very good books in remote sensing for the geological studies. There are many other books, like there are books like this Gary L. Prost, G.L. Prost is very good for geomorphology and hydrocarbon exploration. And there are many more books like Drury's book. There are many other books. Okay. Now, Giri Vishal, what causes earthquakes? So that is a very, very universal questions, no? That is because of the strain accumulation, and plate tectonics can explain. Okay, because the plates, lithospheric plates, are moving with respect to each other, isn't it? Because of this movement of the lithospheric plates with respect to each other, there are different kind of plate boundaries are there, and because of the movements of the lithospheric plates, some strain accumulation at a particular plate boundary happens. Because of the strain accumulation, when the strain gets exceeded their limit, then these cracks develops, and in the crust, this fracture develops, and there is a offset of this crust happens, or displacement of the crust happens, and that is the earthquake. Okay, Nidhi Sharma has asked, what are the mining hazards? So mining hazards, like in case of mining hazard, there are most important hazard is the your land degradation, isn't it? So, but land degradation is not going to cause your casualties, okay? But it is causing the environmental damage, or it is going to cause the property loss. But what is more important is the land subsidence, root collapse. These are important mining hazard, isn't it? Because of underground mining, it happens. Similarly, in case in some of the mines, particularly coal fields, there are mine fire. Coal fire is important mine hazard. Okay, there are many kinds of mining hazards, but these are the important mine hazard which causes casualties, loss of lives. Shreya is asking, can we get more example of de-insert application on urban hazard? Definitely, you can. And that will give you more example during our next lecture tomorrow. Is thermal and microwave remote sensing, what are the advancement has taken place. Then Sunil is asking, okay, how can we detect the sedimentation in ponds or lakes? See, this is not very much a part of geological studies. Okay, but this you can do by this the bands like this ultraviolet band, or this the bands like this blue band, ultraviolet band. In fact, in ocean color monitor, ocean color OCM, okay, we have ocean color monitor in Indian satellites, So there are different satellites hosting this ocean color monitor, so sensor. So using that data, you can have information about the sedimentation in ponds or lakes. But your ponds or lakes should be large enough so that you can get a number of pixels other than the background. Now Nishchal is asking, how can I analyze solar panel glare effects using GIS? Solar panel glare effect. First of all, I have not very much clearly understood your question, okay? And that too using GIS. But from remote sensing, you can get some kind of this sun glint effect you can have where there are the direct reflection happens. So by identifying the sun glint, you can identify where the solar panel is this glare effect is showing. If I have rightly understood, but what I believe that I have not understood your question properly. And then Sam Sinha is asking, can we use geospatial in natural resource management, like increasing soil fertility and its detection? Definitely, you can do. We have specialized courses in these studies, soil nutrients in IIRS. Although we are not doing this particular this research. We have the dedicated soil and agricultural department. Okay, you can contact them. This group is looking after by Dr. Suresh Kumar, and this particular department, okay, Dr. N.R. Patel, okay, Dr. N.R. Patel is looking after this department, soil and agriculture department. You can ask the question directly to him. His email address is available on the website. Either of these two, you can ask Dr. Suresh Kumar, who is the group director of that particular group, or Dr. N.R. Patel. Okay. Then Jyoti Vishwakarma, what role does GIS play in disaster management and emergency response? My God, there are a lot of this low role. In fact, GIS gives you the information system. It gives you where is what. Okay, where is the facilities available? Where is the damage is happening? Where is the manpower? Where is your resource arrangement? All information system is very, very important. It is you can just try to visualize the impact of the information system, isn't it? It gives you all. Where is the route one should follow? Where is the shortest route for the hospital? Isn't it? Shortest route to avoid the flood, for example, if the flood is the hazard, isn't it? So, and for relief operations, so GIS has immense role. And again, Nidhi is asking how to detect mineral under water, like ocean, no? So mineral under water, okay, you won't be able to do that. For that, you have to use some indirect this technique, either by probe, okay, but from the remote sensing image, you won't be able to get it, or some geophysical techniques you have to do. Now, Sahil is asking, why is radar sensitive to moisture content? Why is radar is sensitive to moisture content? Okay, because the radar pulse, when it is moisture content means H2O, and you know the structure of the H2O. It is the distorted what is that sp3 hybridization, isn't it? So if you study this sp3 hybridization, no, this is H2O, how the two hydrogen are aligned with respect to the oxygen. There are two lone pairs and two bond pairs, isn't it?